All right. So number 6 off of the first set of momentum multiple free response questions. Two blocks, A and B, of equal mass are on a frictionless track, as shown. Block A is initially moving with a speed v1 and has a perfectly elastic collision with block B. Block B has a speed v1 immediately after the collision. Yeah. And then it travels around a circular loop of radius r, where r is much larger than the size of the blocks. The speed of the block B at the top of the loop is v top. Block B then slides up the ramp until it comes to a momentary rest at a height h. Derive an equation for that height h in terms of m1, r, v top, and g is appropriate. All right. So initially, the only place I see momentum in this question is in this collision. And it isn't much of a collision because the two masses are the same. And they even tell you the velocity is going to be the same for B as it was for A. So A hits B and stops, and B just continues if it's perfectly elastic, just like A was. So it's really nothing interesting happens here. V1 is still the velocity. It's still the same size block. I'm guessing, I think later on in the question, they may change the mass of this or something. So, but right now, it's as if A1 just kept going. It's the same deal. All right. So they want to include this velocity. All right. Trick on this one. One of the things you want to keep in mind is everything else to me seems like kinetic energy and potential energy. At every point, there's kinetic and potential. In fact, let's map it out. Down here, just before it goes into the loop, we got all kinetic energy, right? Then, anywhere along the loop, it is a mixture of kinetic and potential energies. So at this point, there is some kinetic. It's still moving, right, because it's got a velocity, and there's some potential. But that sum, that mechanical energy at the loop, is the same as the mechanical energy here at the bottom. And it's the same as the mechanical energy here, because there's no friction. We'll call this top. So the mechanical energy at the bottom equals the mechanical energy on the loop, has to equal the mechanical energy at the top. It equals the same mechanical energy everywhere. It's just, here it's all potential, here it's all kinetic, and here it's some of both. Well, let's start filling in what we know for some expressions here. So for example, let's start with that mechanical energy at the bottom. Well, that would be all kinetic, so it would be 1/2 m, m is the mass of either one of these, times v1 squared. All right. And that's all the mechanical energy at the bottom, which means this is equal to this, and it's equal to this. But we're not allowed to use v1. Notice that? We have to use v top, because otherwise I could go straight from here to here and use v1, and I could give you an answer. So we'll continue on. Mechanical energy at the top of the loop there. So I use top for this. That's not good. I'll use highest point. I call loop. I'm still going to call this loop, but I'm going to call this highest point. All right, up here, highest point. All right, because just doesn't, if I call it top, it gets confusing with the fact they use that. So on the loop, you have two forms of energy. You have the kinetic energy and the gravitational potential at that point. Kinetic energy is pretty straightforward. 1/2 the mass times what they call v top squared. The potential may not be as clear, but once you realize that its height is a diameter, it is 2 radiuses. So you're allowed to use r. So it's 2 radiuses. So our potential energy here is the mass times g times 2r. So that's one of the tricks for this problem. They deliberately put the radius over to the side, but this is a radius and so is this. So the height of that block is 2r. It's probably the trick in this problem. All right, and then the mechanical energy at its highest point is all into potential, so it's mg h, and we're looking for h. So all of these are equal to each other. I guess I really don't need this then, do I? I think V top, M, same M here, G I'm allowed to use R. So I think I can simply set this equal to this and solve for H. Let's see what happens. Interestingly enough, maybe not super interestingly enough, the M's are going to cancel. They often do in these cases. So it's just funny because they say you're allowed to use it, but it's going to disappear. So let's divide everything by M, get rid of that. And I'm going to multiply everything by 2 to get rid of this 1/2. So I'm going to end up with V top squared plus 4GR, because I divided by the M, and I multiplied everything by 2. So this 2 times the 1 I multiplied by gave me the 4, equals 2GH. All right, I'm going to divide everything by 2GH, and I'm going to get, let's see, not 2GH, just 2G. H is equal to V top squared plus 4GR over 2GH. And I believe I'm all right. Fundamental constants, 2 is allowed. I put the H down there. I said it, and then I said don't do it, and then I did it. This H doesn't belong there. It's right there. Let's see. GR, VTOP, yeah, everything is kosher here. So this would be perfectly fine. I would not try to simplify anything just because why? That's right. You're good. All right, so there's part A taken care of. So it turns out we really didn't need this initial kinetic energy. We had enough by relating the situation here to the situation at the top. That's everywhere on here, that's to have the same mechanical energy. Okay, let's look at part B. Suppose that the speed V1 of block A is doubled. Well, will the final height of the block B be greater than, less than, or equal to 2h? Ooh. All right. So what's tricky here is we did this first part in terms of the V top, not V1. I would be curious to see how changing V1 is going to affect V top, because that might help me discern what's going on. Or maybe getting V top in terms of V1 or something like that. So let's see. I know that initially, so this is before we doubled anything, all right? It's kind of like a before and after. So before, I had mechanical energy at the bottom has to equal the mechanical energy on the loop. Has to equal the mechanical energy at the highest point. And this is all still using V1. I haven't doubled it yet. And I knew that 1/2 mV1 squared equals, and then this was 1/2 mV top squared plus mg2r equals mgh. So this was the initial situation. And in the last part, we only really dealt with these two parts here and here, but I'm thinking we're going to look at all of them. So I am doubling this. I can't change, so let's look at these two now. If I double this, I can't change the size of the loop. So and I can't change the mass. So the only thing that's going to change is this. So let's look at the effect that doubling this has on V top. Let's see how many times faster it's moving, and then we'll be able to go to the last part, I think. Or can we set this equal to this? Because really they are equal to each other. Maybe that's a simpler way to go. Let's try that first. So 1/2 mv1 squared equaled mg, the original h. All right. This is the before. And we're looking for h, so let's do this. 1/2, the m's are going to go away, so v1 squared over 2g equals h. Now, if I solve this for h, this is the before. Afterwards, the next scenario, I double v1, like they tell me here. Make sure speed went down. Okay. Oh. No, we're good. The masses are still the same, so B is going to... I worried for a second that the collision would be different, but it doesn't matter. If you double this velocity, they're the same mass, so B is going to pick up that same velocity. So we're all right. I almost panicked. So they doubled it. So we know that it's going to be 2v1 squared over 2g equals h, and this is going to be 4v1 squared over, so it's going to be 4v1 squared over 2g equals h, and this is going to be, let's see, we want to look like this, so I can pull out a 2v1 squared over 2g, right? Because if I divide, I'm not going to divide this out. I'm actually going to pull that 4 out. It's a 4. All right, because if I pull, I'm not going to divide because I want this. I want to see that here because that is equal to h. So I'm going to pull that 4 out and say that's equal to the new h. So I should put new. So this represents the old h. 4 times the old h is the new one. So you're going to go not 2 times higher, but 4 times higher. So what do they say? Suppose the speed is double. Will the final height of block B be greater than, less than, or equal to 2h? It should be greater than. And your quick way is saying if you double the velocity, you're going to quadruple the kinetic energy. So it's going to quadruple the potential energy up here. That would be the quick way to do it. So you really don't even need all this. You could say, once again, 2 times the velocity here means, because of the squaring, 4 times the mechanical energy, right? And that means you have 4 times the mechanical energy here, except the only way this can increase its mechanical energy is by making h bigger. G is, you can't mess with it. So therefore, h is going to be 4 times larger. There's a quick version there. This way isn't bad either. All right, let's see what they can mess with now. Blocks A and B, both of mass m still, are moved to a different frictionless track as shown. Let VA be the minimum initial speed for block A that allows block B to make it over the hump of the track. Okay? So I would equate that to basically the potential energy here is equal to the kinetic energy at the beginning. Technically it would stop, but that would be like the boundary point if you had any more. So we'll go with that. So they both have the same mass. So it would all be transferred to this. So the kinetic energy of B here, 1/2 mVA squared, is equal to, we're going to say equal to the potential energy here. Just maybe a touch more, but we'll say equal to, which would be mg height of this thing here. Block A is then replaced with a larger block, block C. which has double the mass as shown. Block C makes a completely inelastic collision. Ooh, wait a second. Inelastic collision with block B so that both blocks stick together and travel along the track. What is the minimum? I'm just trying to see what all this makes sense. What is the minimum initial speed, VC, that block C must have so that the two-block system makes it over the hump? Express your answers in terms of VA. Oy. Okay, so the minimum energy to get over is this. I need the energy, kinetic energy here, to equal this kinetic energy here. Because this kinetic energy, if you calculated it, would be the same number that this is. Just you don't know H or anything. But this is the energy needed to get over the hill, period. So I need the energy here, after these stick together, to be equal to that, or just a little bit greater than it. So let's see. I need 1/2 mVA squared to be equal to, now these two would combine to, it's an inelastic collision. Ooh, so we got momentum to deal with. So initially, so we come off to the side, before I get to that energy piece, we got to do some momentum work. The momentum before has to equal the momentum after the collision. The momentum before is all in the form of C. So it would be, C's mass is 2 times the mass. So 2 times the mass times VC would be the initial momentum. Afterwards, it would be 3m, because it would be C's mass plus 1 of B, which has just m, times velocity. I'm going to call that final, how fast the whole system's going. All right. So, and they're together. So, but this is what I really want. I want this velocity and mass are what I want. But I need it ultimately in terms of VA. But we got this. We got this. So let's see. M's are going to go away. 2VC equals 3V final. All right. And they want to know VC in terms of, so the V final, so over here, I'm going to use this V final because that's the actual velocity it's going to have once they collide and are headed up the hill. So I'm going to temporarily call this, yeah, we're going to do this. We're going to see the energy here is be 1/2. What was the total mass? I don't want to lose it. 3m. I'm going to need that here. The m's are going to cancel again, but it is important. They've combined. Times V final squared. All right. The m's go away. I got VA squared over 2 equals, oh, you know what? The halves go away too. Let's get rid of them. So VA squared equals 3V final squared. But we need to know what VC is in relation to this. But that's all right. We have a connection over here. V final is equal to 2/3 of VC. If I just divide both sides by the 3. So this is V final. So I can bring it over here. I can say VA squared equals 3 times 2/3 VC squared. And then I solve this thing for VC in terms of VA. So we'll sneak that up here. So I'm going to, let's see, square this down here. So I got VA squared equals, let's see, I'm going to have 4 in the top, but a 9 in the bottom of 3. So that's going to be a 3 stays in the bottom. So I'm going to have 4/3 VC squared once I settle all this. And I'm going to take the solve for VC. So I'm going to multiply by 3/4. So 3/4 VA squared equals VC squared. and then take the square root. So I have VA times the square root of 3 over 2 equals VC. So I have an energy situation, and I have the momentum to look at there. And I believe, well, hopefully that's right. I actually don't have the answers in front of me, so I may have to do an addendum for this at some point. All right. If you look up the answers and you see that I made mistakes, please send me a message for the 2 of you that might watch this.